So for gas laws, here we have PV equals nRT. This is an important equation because this equation pretty much covers the equations that we are going to be studying in this particular class. So let's go back to the phase of matter. This is where we're going to be concentrating the gas phase. But remember, we have solid, liquid, and gas. There's actually a fourth phase. And that fourth phase actually exists in most of the universe, and especially the sun, and that's called plasma. The plasma phase is when you take matter and you strip its electrons. So all you have is matter with its nucleus, but its electrons stripped, and that's the fourth phase of matter. Because the conditions here on Earth are not that harsh, we don't have plasma, except, yes, someone got that right. Plasma is the fourth phase of matter, and except for our plasma TV, but even then, plasma TVs are rare these days, we have OLED, organic light emitting diodes, is what we have in our TV. But plasma TV used to be very popular in the early 2000s. But anyway, that's the fourth phase of matter. And the reason why we have phases is because intermolecular forces. It's very strong for the solid. You start loosening it up when you get to the liquid, and then they don't even exist in the gas because they're separated. When you don't have intermolecular forces between chemicals, then they stay separated, and what you have is a gas phase. So as I was saying in the previous chapter, we owe the fact that we have the solid and liquid phase existing due to intermolecular forces. Okay, and that's a cartoon showing how these things are arranged. So let's take a look at this real quick. When we're studying gas, we're looking at what's around us, and what's around us is a lot of gas chemicals. In fact, air is composed of mostly these gas particles, mostly oxygen, nitrogen, but we also have water vapors, carbon dioxide, a cause for global warming. We also have organics like methane. We have trace gas like some argon, and maybe some contaminants out there like carbon monoxide, especially if you're near a car exhaust. But the pressure that we feel here on Earth is actually based on the gas that is directly on top of us. Okay, the gas directly on top of us is actually influenced by the gravitational pull of Earth, and because gas have mass, they're going to exert a pressure on the surface and on us. And here at sea level, we say that it's 1 atmosphere. But again, these are the different components of gas in our environment, some higher than most. And then some of these can be contained. And the thing about gas is that gas are considered point particles that are separated by large distance. On the other hand, liquids are already mingling on top of each other. So if we change the volume of the container between a liquid and a solid, okay, a gas will expand because it's free to move around. A liquid will not. Okay, so we can say that gas is compressible. It's when we go from a large volume to a smaller volume, but liquids are not compressible. Okay, liquids are not. Liquids and solid are generally not compressible. One of the properties of a gas is pressure. The others are going to be temperature, the amount is moles, and then the volume. But pressure is defined, if you've taken physics, then we measure it in pascals, but also millimeters of mercury or torrs. Millimeters of mercury and torrs have the same unit or the same increments. PSI is what you find in your tires. When when the tire label says um, maximum pressure 45 psi, that means the pounds per square inch within that tire is 45 pounds per square inch. Okay, that's what PSI stands for, pounds per square inch. Okay, so that's what PSI means. Um, I'm trying to, that's what happens when, here, clear my screen. So as I was saying, the mass of gas overhead is responsible for the pressure we feel here on this planet. Of course, we're in San Diego. We are at sea level, but when we go up to Denver, which is called a mile-high city, there's going to be less gas overhead in Denver than there is in San Diego. That's why the atmospheric pressure in Denver is lower. The higher in elevation we go up, like in Mount Everest, the lower the atmospheric pressure. That's because there's less gas available. And that's why when you go up in elevation, you get oxygen starve. It's not because the oxygen percentage decrease, it's because the amount of gas at higher elevation is less, and there's less oxygen to breathe in. There's less oxygen for you to put into your system. Okay, so that's what's going on here. Now, why did we call one atmosphere 760 millimeters of mercury? The way we figured that out is that if we have a pool of mercury, you have a cup and you have a pool of mercury, and you have a tube that's been evacuated. So there's a vacuum here. There's no gas at all. It's evacuated. And you put that tube in this pool of mercury. This rise, because what will happen is that the atmosphere would be pushing down on that mercury pool, and then it's going to cause that mercury to go up this tube. If it's at sea level, then that height is 760 millimeters. Okay, that's why we measure pressure in terms of millimeters of mercury, because the way we measured pressure um, earlier was based on taking a tube, making sure it was in a vacuum, putting it in a pool of mercury, and watching how high that the mercury level goes up. We know when there's stronger pressure, because there might be a storm, this thing will go higher than 760. When it's a clear day, so you basically have low pressure, then there's going to be less force pushing down on that mercury, so the mercury level drops. Okay, that's how we get 760 millimeters of mercury. So let me clear that. And so you guys probably seen this. These are barometric pressure readings, isobars. It tells you when you read a weather map, which areas in that particular map, which areas in the United States, if you're looking at a map of the United States, have the same pressure. So these regions right here, between these, would have the same pressure. But once you get to another region, then it's going to have a different pressure. And so you could always read whether a storm is coming, because what will happen is that there's going to be a high pressure region, say in Southern California. And so storms are going to be attracted to void, a vacuum. A high pressure region basically means that there's a lot of molecules in that area. So storms are going to avoid that area and get sucked into a place where there's low pressure. So when there's a high pressure region, we basically have sunny skies, and it's going to be pretty hot. But if there's a low pressure region, then the storms get sucked into that region, and we get rains and all that. So that's generally how you can read a weather map and predict whether or not a storm is going to be nearby or not. You just have to look at the atmospheric pressure. And for some people, what happens is that their joint starts to ache. They get these ailments when they kind of see that the ambient pressure is changing, and especially when they get low. It's like if you were going into an airplane. What they do is they they pressurize the cabin so that it'll be the same pressure as the outside. And so some people who go into the planes get nauseated because of the change of pressure that they put in these cabins. But it's basically what happens when a storm comes by. When a storm comes by, there's low pressure, your body might interact with it or might get some aches and pains because of it. And some people just know that, okay, low pressure, there's going to be a storm nearby. Let me go ahead and clear this. Okay, and then move on. So one of the theories that we have is the kinetic molecular theory. Kinetic means movement. So kinesiology, the study of the motion, muscle motion, and things like that. Kinetic molecular theory kind of explains the movement of gas particles, of particles in nature. And so what we have is something called an ideal gas. And the theory says that gas can be considered point particles. They don't have volume, in other words. We consider it as point particles in a volume. So we don't consider it as something that occupies space. And that's because the math works out that way. Of course, in reality, molecules do occupy space, but if we assume that the space between one gas particle to another compared to its size is very negligible, then we can consider it a point particle. We also say that gas are far apart and move in random motion. They're always moving. We say that the collision with the boundary results in pressure because it's going to exert a force in that area, and that's what pressure is, force per unit area. Okay, so the gas will exert a pressure, and that pressure is that pressure is based on the collision of the gas with the wall. And gas do not repel each other, and they do not attract each other. That's because there are no intermolecular forces between gas particles. And gas motion is proportional to the temperature. The higher the temperature, the faster they move. So these are the postulates, basically statements of the kinetic molecular theory that sort of gives you a visual of how gas behaves. Okay. So in terms of seeing an illustration, you can think of gas as billiard balls in a pool table, but they're constantly moving. They're just not static. They're constantly moving and bouncing off walls. So the area of a billiard table is going to be the volume that it occupies, and then it's going to have elastic collision, meaning that when it hits things, the energy is not lost. So we can take this analogy and think of it as point particles in a box, and then we can think of it in 3-dimension. It's moving like that. They're moving in random motion. When they collide, they do not lose or gain energy. And then, of course, we're considering them point particles. The motion is reflected in the temperature. The collision is reflected on the pressure. The boundaries is reflected on their volume, and the amount of particles in there is reflected into their moles. So now we have all the parameters for a gas law. We have the amount, the volume, the pressure, and the temperature. From these parameters, we can develop a mathematical equation called the gas laws. Okay, so before we get into that, again, let me just illustrate to you that gas are very important. In fact, we probably, even though it's the most chaotic form of phase, it's the best understood. because these things behave in a uniform way. Okay, that's why we can express it in terms of an equation. But in terms of your experience in our day, or gases in our daily life, water boils at a lower temperature in Denver than in San Diego. In Denver, it might have a boiling point of 95. In San Diego, it's 100. And again, it's because when you are boiling water, there's pressure from the atmosphere pushing down on that surface. If there's less pressure because you have less atmospheric pressure out there because there's less column of air overhead, then the energy you need to get into the gas phase is going to be lower. That means you don't have to have a high temperature to do that. That's why water boils at the lower temperature in Denver compared to San Diego. Okay. So um, that basically is it. In San Diego, 100 degrees, water boils at 4,400 meters, 85 degrees. That's in Pikes Peak in Colorado. Denver's lower than that. And then in Mount Everest, it only boils at 71 degrees. Okay. In fact, you can get water to boil at 0 degrees if you just take water and then you remove the pressure, so you evacuate it. What you will see is that the water will actually convert into the gas phase. So the lower the pressure, the overhead of the liquid water, the lower the boiling point. As you dive towards, as you drive up the mountain, you probably have seen this. You have a bag of potato chips next to you. It hasn't been opened, and you're probably driving up the Big Bear, and you see that the potato chips starts bloating up, okay, and starts doing that. In fact, if you're in a plane and you have something that is, you have some sort of liquid or some sort of chemical that's tightly enclosed, be be careful, because when you elevate and the pressure decrease, that thing is going to expand, and in some cases it actually breaks the seal, and then you have a mess everywhere. But that's what happens to a bag of potato chips as you go up in elevation. And that's because when it's that potato chip was manufactured, it was manufactured at sea level, and so it looks normal here at sea level, but then there's pressure in here and there's pressure out here. As the pressure gets lower out as you go up, then the pressure in here has to equalize to the pressure outside. The only way it can do that is by changing the volume. Okay, if you ever scuba dive, I do a bunch of scuba diving whenever I can. It's important. One of the cardinal rules that you need to be aware of when you scuba dive, or even when you go diving. Okay, even when you go diving. I'm trying to get my here clear. Is to constantly breathe through your breathing control valve. And the reason why you need to constantly breathe when you make your ascent is because if you are, say, 100 feet down in the surface, then your lungs are going to be are going to be feeling a certain amount of pressure, because there's a column of water overhead that's pushing on you and pushing on your body. So it's causing the volume in your lungs to get small, but because it's equalized based on the gas that you're breathing in, it's okay. But if you hold your breath, okay, your lungs will expand just like that potato chips as you make your ascent, and then you start to rupture your lungs if you don't exhale. So that's what happens. Okay, this is a illustration of what's going on. So if you're breathing from a tank down at 100 feet and you hold your breath, you could do serious damage to your lungs, just like that potato chip could easily rupture. Okay. Yeah, exactly. For those of you who dive, you need to inflate your compressor as you descend. Exactly. So for again, if you ever take lessons on diving, that's one of the cardinal rules that you have to remember. let's go ahead and, oops, sorry. I'm trying to, when I don't have, convert my slides to a, what is it, a 10 by 9 view, then I can't get these tools up here. And it's hard to get that in my iPad. Anyway, when you breathe, let me finish up this particular section and then we'll get into gas loss next time. When you breathe, it actually works based on the pressure and the volume. And it works through something called Boyle's law. So these days, we're very concerned about people who cannot breathe, and we put them in these ventilators. And that's because they don't have, they can't inhale oxygen like they would normally do. But if you were normal, okay, you're okay, like hopefully all of you are, then the breathing apparatus is controlled by our diaphragm. The size of the thorax is going to go up and down, and when it goes down, it increases the volume in our lungs. And because the volume of our lungs is going to have a lower pressure now because it's got more space, then it's got to equilibrate with the pressure outside. That's why the air rushes through our nose and goes into our lungs, because now our lungs have a bigger volume, and then we breathe in air. And then our thorax or diaphragm will relax, and then that volume will get smaller, and it's basically pushing the gas that we've accumulated in our lungs outside. And so we exhale. So this is the cycle of breathing, where our diaphragm goes out and in, and basically when it goes out, we take in the oxygen goes into the alveoli spots in our lungs, and then it gets absorbed by our blood. Okay, and then when the blood comes back here, it dumps carbon dioxide, and then we breathe out the carbon dioxide through our lungs. But if you go into medicine and you become a respiratory therapist, you learn all that, but it's based on gas laws. Okay, atmospheric pressure is 760 millimeters of mercury. Remember that air is about 79% nitrogen and 21% oxygen. That's in the atmosphere. Okay, so 21% of 760 is 159. So when we breathe in air, only 159 millimeters of oxygen is actually going into our lungs. That represents 21% of the air that we breathe. You can see why we have a hard time breathing at higher altitudes, because then the pressure is lower. This might drop down to 700, which means the amount of gas available to take in is going to be lower. So again, a little bit of how these things relate to our everyday life. Okay. Yeah, I know. My iPad, I gotta make sure that when I change these things, my iPad has a full screen and I can't see these things up here. These things over here, the controls. There's controls here where I can make it into a blank screen and change my pen size. You guys probably can't see it, but it's there. So I'm going to stop there because I want to cover these things next time. And these are the ideal gas law equations, or the gas law equations that gives us ultimately PV equals nRT. Okay, so I'm going to stop there. That seems to be a good stopping point, and then we'll hit the math in Thursday's discussion. So in terms of, we already talked about the kinetic molecular theory, but I do want to talk to you about expanding the kinetic molecular theory. And the kinetic molecular theory talks about properties of gas. I think we covered that last time. We talked about, and if you have these properties for matter in the gas phase, pressure, volume, amount is moles, and temperature, then you can define its behavior. You can define, for example, If you know the pressure, the amount, and temperature, what the volume it will be, what volume it will occupy. If you have the pressure, volume, and temperature, then you know how much gas will be in there. And so that's the whole thing about gas laws, is that even though it's the most chaotic state, with the exception of plasma, of course, but it's the most chaotic state of matter. It's also the most understood because when we're talking about gases, and remember, we're talking about ideal gas. Ideal gas has a behavior that obeys the kinetic molecular theory. In Chem 200, you're going to deal with real gas. And when you deal with real gas, you're going to have to take the ideal gas law, which we will be discussing here, and modify it slightly. The modification is that gases are not point particles. Okay, they're not point particles. And so you're going to have to adjust the volume for real gases, and that the pressure is actually going to be offset, because when gases collide, they do sometimes stick with each other. So in the van der Waal adjustment of gas law, you're going to have to adjust that. But don't worry about that here. I always want to make sure that you guys are aware of what's ahead in Chem 200, because this is looking at the terrain, giving you the fundamentals. But in Chem 200, you go more in depth and you look at a lot of the exceptions and the extensions of some of the concepts we're covering. Okay, so, and besides, in this class, you cover an entire general chemistry sequence in one semester. In the general chemistry sequence, you cover it in 2 semesters. So that's the reason why I always like to give you guys a heads up of what's to come. That way, um, when you see it in general chemistry, you won't be saying that, oh yeah, we never covered that. How come it's brought up here? Well, that's because general chemistry 200, 201, we go into more details. So if you understand that the gases are defined by these properties, then you will understand something called Boyle's law. And Boyle's law, if you think about it, is pretty simplistic. If you take a gas, let's just say you blow up a balloon, and now the gas is in a container, a volume, a fixed volume, and the pressure that that gas exert is actually equal to the ambient pressure. It's equal to the pressure outside. That's why it's going to have a certain volume. Okay, so the pressure inside a balloon is going to be equal to the pressure outside. But if you increase the pressure, then what will happen is that, like squeezing a balloon or squeezing something, then the volume is going to get smaller. So what you can see here is that the volume and the pressure is inversely proportional. That is, if the pressure is high, the volume gets smaller. That's what I mean by inversely proportional. So that's basically Boyle's law. Okay, and when you do a thought experiment, you understand Boyle's law, that increasing the pressure decreases the volume, provided, now this is provided, okay? I apologize for these symbols. These symbols should be delta, okay? Sometimes when you make the transition from a regular PowerPoint to iPad PowerPoint, the iPad might not have the fonts. And so that double arrow is not a double arrow, it's a delta. But delta T and delta N equals 0 means that T2 and T1 is equal to each other. It doesn't change. Okay, that means it's not that the temperature is 0. It's not that the moles is 0. Is that whatever temperature you start out with, it's the same temperature that you end up with. That's what we mean by delta T equals 0, delta N equals 0. If you start out with 30 moles of gas, under the second condition, when you're pressing on the gas, that balloon, it's still 30 moles of gas. It's not changing. whereas the pressure does change. The pressure 2, the second condition, is different from the pressure 1. So keep that in mind that Boyle's law works because the temperature and the amount of gas doesn't change. The second law, this is Boyle's, by the way, the second law is Charles' law. And Charles' law, if you think about it again, let me clear this, is about temperature and volume. Well, if you think about this, think about maybe, again, a balloon in a winter's day where, let's say, the temperature, the pressure is constant. That should be delta, okay? And the MOLS is constant. If you're indoors and say the temperature is 25 degrees, okay, you might have some balloon at a certain size. That's the volume. But suppose you're in Minnesota where it's like below freezing and you go outside, what will happen is that the balloon will sort of collapse on itself. And that's because at lower temperature, the volume also decrease. And you can explain that through the kinetic molecular theory, because when you have a lower temperature, that means the gases are moving slower. If the gases are moving slower, then the pressure inside the balloon will actually decrease. But in order for the pressure to remain the same, remember we said that the pressure doesn't change? Well, that means that if the pressure is to remain the same, that means that the volume has to change and the volume has to decrease. Getting less impact or less force from the molecules inside, that if the pressure has to stay constant, the volume has to decrease. That's Charles' law. Okay, that's Charles' law. And that's Jacques Charles right there. And this is not Gay Lussac, it's Guy Lussac, and that's his French name. Guy Lussac said that, well, maybe we can look at pressure temperature um, variables, holding volume and moles constant. And this makes sense when you have a fixed cylinder. All you have to do is think about your soda can or your beverage in let's say you buy a 6-pack, and in the store it's nice and cool, but it's a hot summer day. It's one of the hottest days that we've had. Okay, so you put it in your car. Say you put it in the trunk of your car. Well, all of a sudden the temperature of that soda goes up, and because there's gas there, soda's not pure liquid. There's actually a thin layer of gas because the soda's carbonated. When the temperature goes up, that gas will move faster, and in some instances, it's been known that the container can't withstand that pressure, so it busts. So in this particular case, what you see is that when the temperature goes up, the pressure goes up. So it's directly proportional. Okay. And again, a lot of these gas laws, all you've got to do is the thought experiment and think about common everyday occurrence, and you find out the relationship. And then finally, there's that's Guy Lussac. Avogadro, same guy who gave us Avogadro's number. And this is very simple. If you have an empty balloon or a balloon that's not filled, okay, then it has a certain amount of gas in there. If you blow into it, so you put in more gas molecules in that balloon, then the volume increases. So this kind of tells you that the volume is proportional to the amount. Okay, so all of these gas laws kind of shows you, and again, this is at constant pressure, constant temperature. So what we're looking in these gas laws is only two variables at a time, but we're looking at all the variables that we talked about earlier: the temperature, the volume, the moles, and the pressure. So that's Guy Lussac. Again, this is Boyle's law. In San Diego, if you have a balloon, you're going to feel a pressure of 1 atmosphere. If you take that same balloon and you go to Denver, where the atmospheric pressure is lower, or the classic examples are bag of potato chip. As we go from sea level up to Bear Mountain, it gets bigger. Then you can see that again, delta. This thing should be over here. Delta T and delta N equals 0. Then the volume increases. Okay, at And this is Boyle's law right here. It tells you that the volume is inversely, whenever you see that sign, it means proportion. In mathematics, it tells you the relationship between two variables. It's inversely proportional to the pressure. When the volume is up, it basically tells you the pressure is down, and vice versa. It basically tells you there's an inverse relationship. So that's Boyle's law in a nutshell. Okay. Um, and this is some experimental data. Right here, you have a cylinder. It's got a certain amount of pressure. What happens when you change the volume? Well, when you change the volume and you measure this pressure, the pressure is going to go up. So right here, if you go from 5 liters down to 1 liter, this is what happens to the, sorry, I got that backwards in terms of the scale. Let me clear that. If you go from 5 liters down to 1 liter, then what will happen is that the pressure will increase. The pressure increases as you do that, and that's what you see in this scale right here. It's inversely proportional, keeping the other variables constant. This is Charles' law, and again, if you go from 0 degrees to 20 degrees, so you're heating it up, you're making these chemicals move faster. At the higher temperature, they're going to collide with the boundaries of that balloon with more rigor. It's going to cause that balloon to expand. And in fact, Charles' law, or Charles, was actually the person who kind of gave us absolute zero. He took a bunch of gases, okay, and he measured their volume, and he started to cool the gas. Of course, the problem with gas is that when you cool it to a far enough temperature, the gas, according to what we've already learned, starts to slow down. And as they slow down, they stick together. Okay, so here the gases are far and separate. Here, when the gas slows down, then the intermolecular forces becomes dominant, and then it goes from a gas phase to the liquid phase. So in other words, when you cool down a gas, it starts to condense. In some gases, it actually goes from a gas to a solid uh, directly, and that's going to be the deposition. The opposite of a solid going to a gas is sublimation. Gas going to a solid is deposition, because you're depositing um, the gas into a solid phase. But nevertheless, what happens is that you don't keep the phase the same when you're cooling it down. So what Charles did was that, okay, well, there seemed to be a relationship here. Suppose we ignore the intermolecular forces. Suppose we extrapolate the volume of the gas as we keep lowering the temperature. Is there a limit in terms of at what temperature will the volume be zero? And in all the gases in which he did this calculation, he realized there was a limiting temperature. And that limiting temperature was minus 273.15 degrees Celsius. And so he proposed that at that temperature, matter ceases to have volume. In other words, matter ceases to move. And in fact, we believe we've done experiments today to kind of see that the molecular motion of matter as we start to approach that temperature pretty much is null and void. We've never reached absolute zero. This is called absolute zero, and we call it 0 Kelvin. That's why we have a exact scale for temperature, because we know at what temperature matter stops moving. Now we've come close to absolute zero, hundreds of degrees, but never absolute zero. Okay, it's never, we've never achieved that experimentally, but very close to like decimal points to absolute zero. But anyway, we give Charles the credit for realizing that. Okay, and because we have an absolute scale in terms of temperature, we now use Kelvin. Use Kelvin, the Kelvin scale, in all calculations. Okay, this is very important because if you forget to change the temperature to Kelvin, say you're working with Celsius, even though let's say that we have room temperature is about 25 degrees, and freezing point is about 0 degrees. Okay, in the Kelvin scale, that's 298, and the freezing point is 273. The scale in the Kelvin is exactly the same as the scale in the Celsius. So this difference right here is 25 degrees. This difference right here is also 25 degrees. When you take difference in the Kelvin and the Celsius, when you take the difference, let's say you have an initial and a final, they're exactly the same. But when you take the value, they're different by 273. When you do a calculation and you're using a value, make sure you convert it to this Kelvin scale. But if you're doing a difference, if you're taking, say, a higher temperature and subtracting it from a lower temperature, it's the same in the Celsius and the Kelvin, okay, because the scales are the same. That's not true for Fahrenheit, because in the Fahrenheit scale, the calibration marks are different sizes. You can't say 0, which is 32 degrees, and 70, which is room temperature. That scale is the same, because what happens is that the size on the Fahrenheit scale are different from the size of the Celsius scale. Okay, so you see that a lot when we do the math. Anyway, this is Charles, and here is some experimental data. I already talked to you about it. He extrapolated these volumes for gases, and he realized that there's a specific temperature in the Celsius scale, right here on the Celsius scale, in which matter ceases to have motion. Let's take a look at Avogadro's. We're going to bypass Guy-Lussac, okay? And the reason why we're going to sort of bypass Guy-Lussac is because his is covered as well. But these three laws right here, Boyle, Charles, and Avogadro, can give us the ideal gas law. Anyway, Avogadro's law is fairly simple. If you've got 1 mole of gas and it has a certain volume, let's say 1 liter, then when we have 10 moles of gas, and remember that the pressure and the temperature is constant, then that volume is going to increase. So we can say that the volume is directly proportional to the amount. And so in order to change that proportionality sign, we have to give a constant, and that constant makes it an equality. Okay, that's just the math behind it. So let's put it all together and summarize what we just talked about. We talked about Boyle's law, and this is basically Boyle's law. It tells you that at under one condition, let's say we're in San Diego, at a certain pressure and a volume, okay, then that's going to be, say, equal to a number. If you take that same balloon and you go to Denver, then there's going to be a new pressure and a new volume, but those two are going to be equal to that same number. That's what we mean by the volume and the pressure are inversely proportional. It says that the ideal gas law says that if you have a pressure and a volume here in San Diego, and you bring that same item to a different condition, then they're going to be equal, because there's going to be, if the pressure goes up here, then the volume has to go down. Okay, so it's going to be equal to each other. So this is right here Boyle's law. This right here is Charles' law. It basically tells you that the volume divided by the temperature under one condition is equal to the volume divided by the temperature in a different condition. If you have a certain temperature here in your house, let's say you're in Minnesota, and the balloon has a certain volume, then when you bring it out and the temperature drops, then that volume will change proportionally. But these two are always going to be equal to each other, the same, the volume divided by the temperature. That's Charles' law. It tells you it's directly proportional to each other. And then Avogadro's law tells you that the volume divided by the moles under one condition is equal to the volume divided by the moles under the second condition. That's what this thing is telling you. And in essence, it's telling you that the volume and the moles are proportional to each other. So the key here is that we can now bring everything together. We can say that the volume is, say that it's inversely proportional to the pressure. That's Boyle's law. It says right here that the volume is directly proportional to the temperature. That's Charles' law. It says that the volume is directly proportional to the moles. And if we want to change this proportionality sign so that it's an equal sign, then we have to put a constant in there. And that constant is next week's lab. Okay, that constant is next week's lab. And that constant is called the universal gas law constant. And that's because we want this to be an equality. We don't call that constant K, we call that constant R. So let me just show you that real quick. And when you look at this equation, right here, and we're going to change it to that, where we put the pressure and the volume together, that's called the ideal gas law. Ideal gas law. This is the gas law that you guys will need to remember, because this is the gas law that brings all the gas laws together. It brings all the gas laws together. And this gas law will actually simplify to Boyle's law, to Charles' law, to Avogadro's law, and to Gay-Lussac's law, if you understand how to use it. So R here, remember R, I told you in that previous slide, is our universal gas law constant. So if we take a condition, let's say we measure a gas at 1 atmosphere. Say that we measure a gas at 0 degrees Celsius or 273 Kelvin. Remember, we always have to use the Kelvin scale. Let's say that that gas is 1 mole. What is the volume of that particular gas? Well, that volume for that gas is going to be 22.4. And in order for that to work, we've got to have a R value of 0.08206. And it's got to have these units. Atmosphere is the units for pressure. Liters is the unit for volume. Moles is the unit for amount. Okay, and Kelvin, definitely Kelvin is always used for temperature. So when you see this number, 0.08206, sometimes some books will have 0.0821, okay, because they're using 3 significant figures. I remember it as this number is 0.08206, okay, it just rattles off my tongue. You got to remember the units associated with that. Liters, atmosphere, mole, Kelvin. Because when you get to Chem 201, we're going to convert liters, atmosphere to kilojoules, okay? And when we convert liters, atmospheres to kilojoules, this is not 0.0821 anymore. It's 8.314. Anyway, that's for the future. Right now, you got to remember 0.08206, because that's always the number you would use if you are using the ideal gas law, okay? PV equals nRT. If you want to remember this, we call it PV nRT, okay? Some mnemonic device tells you PV is that equation, PV equals nRT. So how do we use PV and equals nRT? Well, we use it to solve gas law problems. And there's 2 basic types of gas law problems. One in which you only have one condition, So what do I mean by one condition? It means that, let's say that you're shelter in place and you have a gas and you're not moving anywhere, you're not going out or any place. So that's one condition. Say that you have a balloon, you know the temperature, you know the volume, and you know the pressure. You can calculate the moles in that balloon because you have all the variables. PV equals nRT. You're going to solve for N because that's what you're solving for. And so all you've got to do is the algebra. Before I move on, however, let me do a quick math review. It's very critical that you understand how to do the algebra on the fly because you guys are going to be doing this a lot. Okay, the main equation that you guys are going to be looking at is PV equals nRT, where P is the pressure, and that's in atmosphere. V is the volume, and that's in liters. N is the amount, and that's in moles. T is the temperature, and that's in Kelvin. Always, always, always. Okay, always. And then R, of course, is your universal gas law constant, and that has units of liters, atmosphere, per mole, Kelvin. Liter atmosphere is on top, mole Kelvin's on the bottom. But what you guys are going to be doing is you're going to be saying that PV equals to nRT is the ideal gas law. Remember, the gases are behaving based on the kinetic molecular theory. That's why you always hear this word ideal, because it's behaving based on the kinetic molecular theory. That is, they're considered point particles. When they collide, they have perfect elastic collision. They do not lose energy. They do not stick together. That when they collide with the boundary, then that results in pressure. How fast they move is an indication of their temperature. That's the ideal gas law. And whenever you write this equation, you're assuming it behaves in that manner. But this is like for under one condition. Let's say that you take your system now and you go to either San Marcos or Big Bear or Denver. This ideal gas law is still going to operate. PV equals nRT, because gases doesn't care where you are. The variables will change, but that equation will always be constant. So we will call this condition 2. Okay, under different circumstance. And you can label this 2, 2, 2, 2. R is always the same. Okay, so here in San Diego, you have a certain pressure, volume, amount, and temperature. But when you go to Denver, San Francisco, or Mount Everest, you have a different pressure, volume, moles, and temperature. So what you end up doing a lot is you divide condition 1 by condition 2, and you do the math. Well, this right here, when you do that, is a ratio. And so when you do ratio equations, let's say you have A over B equals C over D, a lot of times you've got to isolate the variables. That's what you do in math. Let's say I want to isolate A, and I want all the other variables to be in one side of the equation. Well, in order to isolate A, you have to multiply B by both sides. By multiplying B by both sides, this cancel, and what you have is A equals C times B over D. Okay, that's the long math approach. Let's say that you have, in this equation, you want to isolate D. Say we have this right here, and you want to isolate D. Well, if you want to isolate D, I'm going to change pen. This right here, it's got to be in the numerator. It's got to be on top. It can't be in the denominator. So the way you do that is you multiply both sides by D, and then you divide both sides by A, and you multiply both sides by B. You can see this is pretty tedious, so that the B's will cancel on one side, the A's will cancel on one side, the D doesn't cancel here, but the D cancels here, and what you get is an equation in which the variable d is in one side. Okay, bear with me now because I'm going to show you the trick to do these things quickly. And the trick is the following. If you've got a over b equals c over d, whenever you're going across an equality sign, you're always going from the numerator to the denominator and vice versa. You're always going from the denominator to the numerator and vice versa. So if I want to isolate a in this equation, then what I'm doing is I'm just popping b over here because that's where it goes when it goes across the equality. And so a equals, and this is over 1, c times b all over d. That's the equation I want. You got to remember, when you move a denominator across an equality, it ends up in the numerator. And that's because when you do the math operation, you have to multiply both sides by b. Now, let's say I want to isolate d. If I want to isolate d in this equation, I want to isolate this so that all the other variables are across. Don't move c down here because what you will end up with is 1 over d. That's not what you want. What you want is d in the numerator. So we pop d over here, we pop a down here, and b over here, and what you end up with is d is equal to b times c all over a. So if you remember that little trick, you'll fly through the gas laws really quickly, because what you end up with is you have equations like this. P1 equals V1, P2 equals V2, and you need to solve for the second volume. Well, if you're going to solve for the second volume, pop V over here, pop P1 over here, pop P2 over here, and now what you have is V2 equals V1 times P2 all over P1. Those are the type of equations that you're going to see in gas laws. And in order for you to go quickly in setting up the variables, this little trick will come in handy rather than going through the routine of multiplying both sides by V2, dividing both sides by V1, and etc. Just do that because that's the shortcut of things. Okay? I always like to do that, whether it's your course or general chemistry course. I just want to give that quick reminder of how to do the algebra in gas laws really quickly. Okay, so let's go back here. What happens is that in this particular case, what you're always doing when you only have one condition, you only have P1V1 equals N1RT1. That's one condition. You're usually solving for one variable. Okay, so that's what we see right here. What we see right here is condition 1. You have pressure, volume, moles, and temperature. And usually one of these will be the unknown, and it's up to you to calculate that. Okay, that's condition 1. You're not taking that system and moving it to a new pressure or moving it to a new volume or changing the amount. There's only one condition there, and you have to solve for the other. The more common problem is this right here, where you have one condition here in San Diego and you have a second condition in Denver. Well, in that case, one of the variables will change. Let's say that we have atmospheric pressure in San Diego, but now the pressure in Denver is different. It's going to be lower. Well, how do the other variables change? Okay, how do the other variables change? And this particular condition you want to set up. Okay, here in San Diego, P1V1 equals N1RT1. In Denver, it's going to be the ideal gas law, so we'll call it P2V2 equals N2RT2. Now, in this type of equation, R's are always going to cancel because 0.08206 over 0.08206 is 1. So you don't have to worry about R, they'll cancel. And if the moles doesn't change, let's say the amount of gas here in San Diego is the same as the amount of gas in Denver, then they say 30 over 30 is equal to 1. So anything that doesn't change drops out of this equation. Let's say that the temperature doesn't change. Well, this whole side cancels out. So this whole side becomes 1. And so what you have is P1V1 over P2V2. If you decide to make this equal to each other, P1V1 equals P2V2. Remember, 1 is just a number 1 over 1. So we're going to bring this in the numerator. Hey, this right here is Boyle's law. Okay? When temperature and moles are constant, so they cancel out, you get Boyle's law. So that's what I mean by saying that all you have to do is remember the ideal gas law, because everything else distills down. Those other law, the ideal gas law will convert to those other law when those variables are constant. And you want to set it up under condition 1, condition 2. It makes understanding gas law problems so much easier. This is what you call the combined gas law problem. Combined gas law setup. Anyway, these are the two strategies that you have. Remember that temperature is always in Kelvin. So let's do a quick problem. This is a condition 1 problem. And it says, how many moles of xenon are in 2 liters, 0 degrees, and 1 atmosphere? Well, always convert your temperature, no matter what, to Kelvin. 0 degrees is 273 degrees Kelvin. Remember, this is a condition 1 problem, so P1V1 equals N1RT1. What are we doing? We're solving for moles. So this is over 1, this is over 1. We're solving for moles, we're pushing RT over there. And so what you have is P1V1 over RT equals moles. See how easy that was in terms of doing the algebra? Okay, I'm just making sure that I go across the equality sign. Whenever you have a variable like 23 is equal to 23 over 1. Okay, so you can make it a ratio. And that's what I did here. I put a 1 over this P1V1, and I put a 1 over this N1RT1. That way I can do the math easily. So what we have here is this equation. All we got to do now is pop in the variables. We can say that we have 1 atmosphere. We have, according to this, 2 liters. We have 273 Kelvin. And our R is 0.08206 liters, atmosphere, mole, Kelvin. The liters will cancel out right here. Okay, the liters cancel out. The atmosphere cancels out. You see how this is in the denominator? Kelvins will cancel out. But because the moles is in the denominator of a denominator, the math will make it in the numerator, and that's just N, which is in moles. So if you just crank out this math, 1 times 2 divided by 0.08206 divided by 273, you get the quantity of moles. And let me just show you how that's done. I'm going to clear this. Here it is right here. That's that. That's the equation we just derived. We plug it in. We notice the units cancel except for moles. We crank out our math. It comes out to 8.93 times 10 to the minus 2 moles. Okay. That's how much xenon would be in 2 liter, 0 degrees, 1 atmosphere. We're using condition 1 type of problem. PV equals nRT. PV equals nRT. Right there. Okay, so that should be straightforward. Now let's take a look at a condition 1, condition 2. And you know it's a condition 1, condition 2 problem because now one of the variable has changed. It's not giving you a set of variables to solve a fourth one. Okay, one of the variables has changed. So here we have hydrogen gas. We have hydrogen gas, and it occupies, so we're going to say that's condition 1, V1 equals 2.33 liters. And the pressure is 745 torrs. Remember, torrs is millimeters of mercury, and 760 millimeters of mercury is equal to 1 atmosphere. So we might have to convert millimeters of mercury to atmosphere. Temperature is 27 degrees Celsius. Add 273 to that. Always convert your temperature to Kelvin. That happens to be 300 Kelvin. Okay. So that's condition 1. I'm going to put 1 right here. What is the new pressure? What is the new pressure? That's the question. If the volume is decreased, so the volume is 1.22 liters, and the temperature is raised to 100. Temperature is equal to 100 degrees Celsius. We're going to convert that to Kelvin. That is 373 Kelvin. I'm always doing that. That way I don't forget. Temperature is always in Kelvin. So the question is, what is the new pressure? This right here should tell you. This is a condition 1, condition 2 problem. Okay. Let's take a step back for a moment. We have a gas, 2.33 liters. It's at 27 degrees. Okay. The volume drops down a little bit, but the pressure goes up, the temperature goes up substantially under the new condition. See how this volume right here gets smaller? So what's going on is that the volume is smaller and the temperature is higher. Just using your common sense. If you take a gas and you squeeze it so it has a smaller volume, what happens to the pressure? Well, from Boyle's law, you would say that the pressure would go up just based on that volume relationship. Okay. Let's take a look at the temperature. The temperature goes from 300 to 373. Think about it again. We go from 0 degrees to 373 in terms of the temperature. What do you think would happen to the pressure? Well, the pressure too would also go up. So you would expect an answer. This is what you want to do in science. You want to make sure that you're heading in the right direction. That way, if you make clumsy mistakes, you can catch yourself. I would expect an answer to be higher than this initial one because the conditions, the second conditions indicate that my pressure should be higher. So before you put your pencil on paper, think about the problem a little bit and think about the direction that your answer should be. So there's a question on the chat, does N mean something different or is it another variable that is the same as the moles? Capital N, I don't know about capital N, but when you're talking about amount, it's small n, and that is moles. Okay, so N in the ideal gas laws is moles, and the unit is MOL. Okay, it's MOL. That's the unit, and that's the same unit that we use in stoichiometry. So N is moles in gas laws, exactly. Okay, if you've got Avogadro's number, then N is 6.02 times 10 to the 23rd. So moving on, we now have an idea that this is a condition 1, condition 2 problem. Okay, this is a condition 1, condition 2 problem. Let me clear up some space here. So we know it's P1, let me change my pen. P1 V1 equals N1 RT1. That's the set of conditions right here. We also know that we have P2 V2 equals N2 RT2. Now notice that they don't say anything about the moles of hydrogen. If they don't say anything about the moles, they don't define it, you can assume it doesn't change. You can assume that the moles under the first condition is the same as the moles under the second condition. So if they're the same, they cancel out. You can also see that R cancels out. Once R is not in the equation, once R is not in the equation, then you can change your units for P and V. It doesn't have to be atmosphere, it doesn't have to be milliliters, but the pressure under condition 1, the units, has to be equal to the pressure under condition 2, the units. The volume under condition 1, the units, has to be equal to volume under condition 2. If you're using gallons in condition 1, then your units got to be gallons in condition 2. Okay? Because the only reason why you would use liters, atmosphere, mole, Kelvin is because R is in that equation. And R has a certain amount of units in it. Liters, atmosphere, moles. Temperature always has to be in Kelvin. Temperature always in Kelvin. Okay? You cannot say, okay, I have degrees Celsius up here, I gotta have degrees Celsius down here. It doesn't work that way. Kelvin has to be in, temperature has to be in Kelvin. Anyway, let's go back here because I want to show you how this problem simplifies. We're solving for pressure 2, this guy right here. So we're sending V2 up here. We're sending V1 and P1 down here. Sorry, I got that backwards. I'm isolating P1, V1 equals P2, V2. And remember the N, the R cancels. And so what we have is T1, T2 here. We're isolating P2. So we have to bring P2 here, and we have to bring all the other variables on that side to the other side. So when you do that math, what you have is P1 times V1, and we're bringing T2 up here, and we're bringing T1 down here. Remember, T1 goes down here. V2 is staying the same, and we're bringing P2 up to the numerator. So that's the equation we have. That's the equation we have. We're bringing T2 off to the numerator on the left side. We're bringing T1, because remember, this side only has T1 and T2, to the denominator on this side, and we're putting P2 isolated. So our equation is P2 equals P1 V1 T2 all over T1 V2. Now we can put in our numbers. We can put 745 torrs here. We can put 2.33 here. Remember that T2 is going to be 373. T1 is 300. That's this right here. And then V2 is going to be 1.22. So when we plug it in, this is what we will have. 745 torrs. And let me show you why torrs work. V1 is 2.33. T2 is 373 all over 300 times 1.22 liters. Look what happens. Liters cancels. Kelvin cancels. The only thing that you're stuck with is torr, and that's the unit that you want. That's the unit that you want. That's why you're not required to stay with atmosphere once you eliminate R. You're not required to stay with liters once you eliminate the R. You are required to use Kelvin always. Always, always Kelvin. So here's the setup. I'm going to clear this. This is what we have. This is what's going to cancel out. We basically have this after we cancel out, and then we're going to do the math, and what we have is that equation that I just wrote. Okay, this is only for gas laws. Yes, Kelvin is always, and what other, whenever you're dealing with gases, okay, gas laws, you're always using Kelvin. Okay, so this is basically the equation we have. Now we're going to pop in the variables. And what you have here is what I did See, this is my answer. But if the question is, what is the pressure at under atmosphere, then just take your answer, 770 torrs, and remember that it takes 760 torrs equals 1 atmosphere. You do your dimensional analysis. And when you do that, this is the number that you get. All you got to do is a simple conversion factor from torrs to atmosphere, because remember, 760 torrs equals 760 millimeters of mercury equals 1 atmosphere. And this is equal to 14.7 psi as well. Those are your conversion factor. All of those, 14.7 psi, 760 torrs, 760 millimeters of mercury equals 1 atmosphere. That's your conversion factor for pressure. So hopefully you guys got this down, because that's what we're going to be doing for the rest of this. Generally, your gas law problems are condition 1, condition 2. But before you put your pen on paper, think in terms of whether the variable is going to be higher than the original or lower than the original. And indeed, 1770 is much more higher than 745. As we predicted, the pressure should go up compared to condition 1, because the temperature is pushing you in that direction, and the volume is pushing you in that direction. Okay, it's kind of like gauging your ballpark estimate. A lot of scientists will always look at a problem, do the math quickly in their head, and come up with a ballpark answer. So when you guys do a science equation, if you have enough background, do the quick calculation in your head, or think about the scenario and think about where that final answer should be. And if you get for example, if you're calculating a temperature and you get something like negative temperature, well, you know that answer is incorrect, because you can never get a negative Kelvin. Okay, you can never get a negative Kelvin. So what is 53? I don't understand that question. Okay, 77. Oh, that's. Let me double check my answer. Maybe 1770 divided by 760. Yeah, that's 2.33 atmosphere. Okay, so I don't know what that comment is in the chat. The 0053. Okay. Oh, okay. That's just a typo in the chat. That's fine. So let's take a look at more problems in this manner. Here's another problem. And this is actually a Boyle's law problem, but we're going to set it up using the ideal gas law. Remember, I told you, if you remember the ideal gas law, then it distills down to the other gas laws, because the variables will cancel. Let's take a look at this right here. So that's a volume. That's 6.50 liters. Oxygen is our chemical. It's at temperature 124 degrees. We're going to add 273 to that right away so I don't forget. That's 297 Kelvin. Is underwater at 1.5 atmosphere. That's pressure 1 equals 1.5 atmosphere. Okay. If the balloon is moved to a lower depth, so what we're doing is we're moving this balloon to a lower depth, such that the pressure is, so pressure 2 equals 2.50, and that makes sense. When you start to submerge, there's going to be a greater column of water overhead, and so the pressure will increase. Okay, such a pressure. What is the new volume? So the new volume is 2. Notice they don't say anything about the temperature, so you can assume that the change in temperature is 0. Notice they don't say anything about the amount, so you can assume that the amount, if they don't say any new condition for that variable, you can assume that it doesn't change. So when you have P1 V1 equals N1 RT1, and we divide that under the new conditions, and we start eliminating the variables that stay constant. N stays constant, T stays constant, R stays constant. When you have a constant over a constant, it's like 20 over 20, that equals 1. Okay, it doesn't go to 0. When you start um, canceling out this variable, that doesn't go to 0. It goes to 1 because the numerator is equal to the denominator. So 20 over 20 is 1. 1 million over 1 million is 1. So what we have is P1 V1 over P2 V2 equals 1 over 1. What are we solving for? We're solving for the new volume. Bring the new volume to the other side. What we have is V2 equals P1 V1 all over P2. This is the equation we're going to be using. That's Boyle's law. This relationship right here is Boyle's law. When P1 V1 over P2 V2 equals a constant 1, that's Boyle's law. Anyway, this is the variable that we will be, this is the equation we will be solving. All we've got to do now is pop in, we got to pop in 1.5 atmosphere here. We got to pop in 2.5 atmosphere here. We got to pop in 6.5 liters there, and we can solve for V2. So when we do that, okay, see, I give you an illustration. The balloon goes from a bigger size to a smaller size. So you know the volume's got to get smaller. And it makes sense. It makes sense. So let me go ahead and show you this. These are the variables. Notice the temperature is constant. So that doesn't even play a role in this particular problem. Here's the math. Okay, this thing is constant, and so this is the equation we have. Or we could have left P2 down here, put V2 over here, and that is basically the setup. And when we solve this math equation, we get 3.90 liters. And it makes sense. The volume is going to get smaller. It's going to go from 6.5 to 3.9 because the pressure is larger. Bigger pressure means that you're squeezing the volume to a smaller size. Let's move on. Here's Charles' law, again through PV equals nRT. A gas occupies 2.22 liters, 0 degrees Celsius. To what temperature must the sample be heated to occupy 3.22 liters at constant pressure? So delta P and delta N are both equal to 0. That is Charles' law. Let me just show you how that works. Okay, so again, some of my dramatic effect. When you heat up something, then of course it's going to increase in size. So you would expect the volume to be larger than 3.22. That's the direction we want. So let's look at the math. Here it is right here. You set up all the variables, and then you do the math. What will cancel out? N will cancel out. R will cancel out. P will cancel out because it doesn't change. So what you have here is V1 over V2 equals T1 over T2. Remember, you're solving for T2 here. So when you arrange that, that's the simplification, getting rid of everything. When you do that, T2 goes on top, V1 goes on the bottom, V2 goes on top. Remember that the variable you're isolating always has to be in the numerator. I can't stress that enough, because if you solve this equation and you put T2 on this side and put V2 here, your answer will be the reciprocal of the temperature. That's not the correct answer. That might be a choice in a multiple choice exam, but that's the wrong answer. And the reason why it's the wrong answer is because your unit is reciprocal Kelvin, not Kelvin. It's got to be in the numerator. It's got to be on top shelf. Okay? So remember that when you do your algebra. You certainly need to isolate the variable, but you got to make sure that the variable is in the numerator. It's on the top shelf. So once we do that, then we just plug in our value. Notice that we've converted our temperature to Kelvin. So our answer will be in Kelvin. If you want to convert it to Celsius, then you subtract 273 from that. And indeed, what happens is that it goes from 0 degrees Celsius or 273 Kelvin to 123 degrees Celsius or 396 Kelvin. Definitely higher. And that's because you're heating it up. You're heating it up, the volume expands. I'm going to switch gears here because I want to tell you about something called STP. STP means standard pressure temperature. And you might say, what's so standard about the pressure and the temperature? Well, when we do an experiment, let's say we do an experiment here in San Diego, and let's say that the school's open and you guys are doing gas law problems, and you're trying to mimic, say, a gas law experiment in Denver. Well, what you'll find out is that your numbers might be different. And the reason why they're going to be different is because your conditions are different. So if you're comparing answers, but your conditions are different, then you've got to make that adjustment. What scientists have done is that they've defined a standard pressure and temperature so that if you want to verify a result or you want to publish a result, then you do it under these conditions. That way people can mimic your experiment. And the standard pressure and temperature, you want to put the pressure, change my pen here, you want to set the pressure at 1 atmosphere, and you want to set the temperature at 273 Kelvin. That is standard pressure temperature, STP. Now, we can disguise this and say, okay, let's do the pressure at 760 torrs and 0 degrees Celsius. You have to recognize that 760 torrs is 1 atmosphere. You have to recognize that 0 degrees Celsius is 273 Kelvin. Let's say that we want to do this at 14.7 psi and 32 degrees Fahrenheit. All of these are STPs. Okay, all of these are STPs because if you convert 14.7 psi, that's 1 atmosphere. If you convert 32 degrees Fahrenheit, that's 273 Kelvin. So right away, even though they have different units, these are all STPs, standard temperature and pressure. And the neat part about standard temperature pressure is that if you define your pressure and your temperature, and let's say we use 1 mole of gas just for convenience, then we can solve for volume. We can do this. PV equals nRT. We're going to define 1 mole of gas. We're going to isolate the volume. If you solve that, that comes out to 22.4 liters. At STP, 1 mole of gas is equal to 22.4 liters. 2 moles of gas is equal to 44.8 liters. 3 moles of gas will equal 66.2. This will be 67.2. Clear this. 67.2 liters. In other words, we can use that as a conversion factor. Okay. No, 1 atmosphere does not equal 273. 1 is a pressure, 1 is a temperature. They do not equal each other. Those are conditions. Okay. So make sure you understand. 1 measures the force per unit area. The other measures the energetics of a chemical. These are variables. But under 1 atmosphere, under 273, we have STP. That's what STP means. So the reason why I'm giving this to you right here is that let's take a problem. Okay, let's take a problem. Let me clear this real quick. Okay, here it is right here. That's it. So let's just use that knowledge to solve a problem. Okay, here's the problem. How many moles of xenon are in 2 liters, 0 degrees, 1 atmosphere? Right away, you should recognize that's STP. Okay, so we have 2 liters of gas, and we want to figure out how many moles that is. Well, rather than PV equals nRT, putting your pressure here and your temperature here, what we're going to do is just use the simple conversion factor. We're going to say that solving here for the moles, we're going to say that 22.4 liters is 1 mole. That's our conversion factor for STP. 22.4 liters equals 1 mole. And so when we do this, the liters cancel out and we have our equation. You don't have to go through the gas laws. In other words, you can just use that conversion factor, but it only works at STP. Okay? It only works at STP. You want to make this assumption: 1 mole of any gas. It could be xenon, it could be methane, it could be oxygen, will occupy 22.4 liters at 1 atmosphere, 0 degrees Celsius, 273 Kelvin, any gas. So when we do this, okay, when we do this, let me clear this real quick so that you guys can see the math. Okay, there it is right here. And what we get is 8.93 times 10 minus 2. Look back in the first example we did, okay, a couple of pages ago. Let me just show you that real quick. Okay, let me get out of here real quick. And we are here. We're going to discard that. Let's look at this first problem we did. Remember this first problem we did where we used the ideal gas law? We got 8.93 times 10 minus 2. Here we're using STP. Oops, here we're using STP. Where am I? Okay. Here we're using STP right here. Let me find where I am in my, let me go back because I actually have it in the next slide. This is STP, and this is what we did from the previous problem. It gives us the same answer, except one was much faster than the other because we can use that conversion factor. 1 mole will occupy 22.4 liters at STP, okay, at STP. So I'm going to switch gears now, and we're going to use the ideal gas law to figure out the molar mass of a gas and the density of a gas, okay? Remember that gas, matter, is going to be in here. And because different chemicals have different molar mass, we can actually figure out how to determine. In fact, there's an equation that we do. Maybe you guys do this in 200. You don't do it in 152. That if I can take this gas and weigh it, if I can weigh that gas and get a mass of that gas, and you might think that gas don't have mass, but it's matter. Matter occupies space and volume, and matter is going to have mass. So if you take, for example, a balloon, and you have a very sensitive scale, you put the balloon, the empty balloon, the deflated balloon on a scale, and you weigh that. And the next thing you do is you take a balloon and you pump it up with your gas, carbon dioxide, and blow into it, and you put it on a scale. That balloon will weigh more than the deflated one when it's empty. That basically is the mass of that gas in that container. Likewise, helium, it too will have mass. And you might say to yourself, then why does it float? And the reason why it floats is the same reason why if you take an object like a piece of wood, a balsa wood, and you put it in water and you put it underwater, it floats to the top. The reason why it floats to the top is that the density of that wood is less than the density of water, so it goes to the top. Helium has a lower density compared to the atmospheric gas around us. And so what happens, because it has a lower density, it's going to start floating. Okay, so that's the reason why you might think that helium is weightless. It actually has mass because it's under the influence of gravity, but what happens is that it floats because in this sea of gas that we have, it's less dense. Okay, so you don't want to blow in helium gas when you're weighing this because you've got other factors to consider. Okay, but carbon dioxide definitely is a much more massive, heavier, and it's much more dense than oxygen and nitrogen, and so it'll sink. But anyway, let's take a look at this. If you have the grams, if you have the mass of a gas, then all you need to do is calculate the moles, because remember, what is molar mass? Molar mass is grams per mole. Like oxygen, it's 32.0 grams per mole. So let's say we have this unknown gas and we weigh it, and now we're trying to calculate the moles. Well, we can calculate the moles by PV equals nRT. Okay, we're going to solve for n here. And so when we do that, we say n equals PV over RT. So we can come up with an equation and say that, okay, if we combine these things together and say that if we have the mass of the gas, this is mass, and we divide it by PV over RT, then that is equal to the molecular weight. So I'm going to simplify this, and I'm going to substitute M for mass. I'm going to put PV down here. And then remember that this is in the denominator of a denominator, so that automatically goes on top. Well, that's our equation for molecular weight of a gas. The molecular weight of a gas is equal to the mass of that gas times R times temperature. Temperature has to be in Kelvin, divided by pressure, divided by volume. Okay? And that's basically what you see right here. So we can calculate the identity of gas. This is actually a pretty cool experiment if you can do that. Here we have it. Okay, so that's basically this equation right here, and that's the equation that you can use. The mass times RT divided by PV. Now let's figure out density. Density is grams over volume. Okay, grams over volume. It's the mass divided by the volume it occupies, like the density of water. 1 gram per 1 milliliter of volume is the density. Well, look over here. Let's take a look at this mass and this volume. So the molecular weight is equal to the mass, M, times RT all over PV. What we're going to do is isolate this variable right here and send everything to the other side. When we do that, the molecular weight times RT divided by, oops, I did my math incorrectly. Let me erase a couple of things. R needs to go in the denominator. R needs to go in the denominator here. This is RT. It needs to go in the denominator. So RT is on the bottom. And P needs to go in the numerator. And what we have in the other side is M over V, which is density. So the density of a gas can be determined based on the identity of the gas times the pressure it occupies divided by RT. And you see that here. You see this in this equation. Let me clear this so that you guys can see that. In other words, yeah, I'm deriving these equations for you, but I want you to see that the gas laws are really useful concepts because it gives you these other variables. Okay? So basically isolating mass over volume, which is density. This is density right here. And I do that by moving P onto the other side, where M is the molecular weight now. Okay? And then RT on the other. So these are ways, if they tell you these variables and they ask you to calculate the molar mass or the density, you can use these equations. And it comes directly from the ideal gas law. It comes directly from the ideal gas law. Okay? So the molar mass of gas, what is the molar mass of 3.54 grams gas, 1.56 atmosphere, 1.74. So remember that the molecular weight, the molar mass, is equal to, let me take a look at that, mass RT over PV. So mass RT over PV. We can say the mass is 3.74 grams. R is 0.08206 liters atmosphere mole Kelvin. I'm carrying the units of R so you can see how they cancel. T is 25 degrees is 298 Kelvin. All over pressure is 1.56 atmosphere. It's got to be in atmosphere. Why? Because we're using R. So you got to make sure your pressure and your volume are in atmosphere and volume, because otherwise the units will not work. And the volume is 1.74 liters. So the liters will cancel out, the atmosphere will cancel out, the Kelvin will cancel out. What you end up with is grams, and this is in the denominator here. You end up with grams per mole. So when you do that math, okay, when you do that math, I told you, gas laws are intense in math. So don't say I didn't warn you, okay? Here it is right here. We cancel it out and we get 31.9. And if you think about this, what gas common in our atmosphere has a mass of a molar mass of about 32? That's oxygen. So this is probably oxygen. O2 is 32.0 grams per mole. Okay. What is the density? Well, the density is just going to be equal to the molar mass divided by the volume. So you can actually go back to this previous problem right here. The molar mass was 31.9, the volume was 1.74, okay? And you can cheat that way. You can say that it's, what is the density? 31.9 grams per mole. The volume is going to be, the mass is 3.54 and the volume is 1.74. You can actually calculate the density that way. But if you were not given the mass, you were given only the molecular weight, then you would have to go through a various problem, and this is how you would do it. Sometimes there's a tricky way to answer these things. Sometimes there's a difficult way, but I want to show you this real quick. Okay, what's going on here? Here it is. Okay, 31.9, pressure is 1.56, RT is that, and you get 2.03 grams per liter. But if you take 3.54 and you divide by 1.74, this is grams, this is liter, you actually get that same number. Okay, so there's different ways of coming up with the same thing. Here, of course, you would need the mass of the gas, but if you were not given the mass of the gas, you were given the identity, then that's the approach you would use. Let me just see the time. Let me wrap this up. Yeah, that's a good stopping point, actually. Next time, we're going to use this portion of the stoichiometry map, because remember, through PV equals nRT, we have moles. And as long as you have moles, you can do stoichiometry. Okay? So more math ahead, and we're going to take our concept and we're going to be able to put in stoichiometric relationship. Because when you carry out a reaction, you don't always carry out a reaction in the math phase, in the aqueous phase, okay? You might have to carry out a reaction in the gas phase. And always through stoichiometry, you have to go through the moles. There is no way around it. You have to go through the moles in stoichiometry. And in the gas law, you have a stoichiometry parameter. That's the key. Once you get to the number of moles, then the rest is based on what you guys have already learned. Yes, there's a lot of math here, okay? And that's why I'm not putting it in this quiz that's coming up, because you already have enough concepts in your head to kind of like sort out. If I threw this in this quiz coming up, you'd just be sort of, you need some time to digest it, in other words. So it would be unfair for me to put gas law problems here when we just completed it. You need time to like have it soak in so you can make sense of what we're talking about. Okay, so I'm going to stop there, and I'm going to open it up for any questions that you guys might have. If you guys can unmute yourself, you have questions, or write it up. If there's no other questions, then for those of you in lab, I will see you at 3:30. That's when it's scheduled in Zoom. Let's see, got it. We are, yeah, you exactly. You are sponges. You need to absorb these things, and you got to retain it for 200, or at least have it in the back of your mind. It might not come as fast to you in 200, but because you've learned it already, you're going to find that relearning these things are going to be much faster. I think I left off with this particular chart, and you guys should be familiar with this chart in terms of this right here. We covered this part right here, where we had the mass of a substance and we calculate its moles from the molar mass. And then we relate one moles of chemical to the other moles of chemicals through the balance equation. And then once we have the moles of another chemical, say a product, then we can calculate the mass using the molecular weight of that substance. Or we can calculate the number of atoms or molecules using Avogadro's number. So what we're going to do is we're going to expand to this portion of this stoichiometry map, this right here. And as long as you can calculate moles, you can do stoichiometry. And stoichiometry is just a series of calculation that allows you to calculate how much product or how much reactant you need if you have certain conditions, like you start out with a certain mass or certain volume of gas. You can figure out how much product you're going to end up with. Or if you want to know that how to generate X amount of product, how much starting material do you need? So you guys learned all that back in chapter 7 and 8. Okay, and hopefully you haven't forgotten too much. And try not to forget too much. I know that it could be overwhelming, but you guys are going to have to remember these concepts for Chem 200. So yeah, it's going to be much more difficult learning Chem 200 online. So you want to be comfortable with it when you're seeing it here, because chemistry 200 is a lot like what we're talking, except it goes probably a layer or two deeper. So but if you remember the core that we've discussed here, it'll be easier to remember. Remember that learning is much easier the second time around if you are familiar with the concepts. And hopefully that's what we're doing here. You guys are getting comfortable with the concepts so that when you do see it in Chem 200, you'll be able to relate to the fundamentals and then dive in deeper as the topics go in deeper. But like I said, the discussion today will be very pertinent for those of you who have lab. So we start out with this just to give you an idea of what the lay of the land is, okay? So here's a question right here in which we do stoichiometry using gas laws. And you guys should be familiar with this problem already, because we've done this calculation twice in the last discussion, the last lecture. And now we put in the context of stoichiometry. It says right here, xenon will react with fluorine. Here it is, according to the following reaction. Whenever you see a reaction, please make sure that it's a balanced equation, because don't ever assume that an equation that you see in the test is balanced for you. You have the skills to balance it or to double check it, so make sure that it's balanced. First of all, remember that when you balance it, make sure that the chemical formula is sound. And then once the chemical formula is sound, that is, it makes it's correct in terms of the charge and things like that, then you can balance it, because then you're balancing the correct equation. Anyway, it says right here, if you have 2 liters of xenon gas at 0 degrees and 1 atmosphere, and you should remember that that's STP, standard temperature pressure. Whenever you see this condition, then you know that 1 mole of gas has a volume of 22.4 liters. That's always the case under standard temperature and pressure. Whether they give it to you at 0 degrees, 1 atmosphere, or 273, 760 millimeters of mercury, those are all the same conditions. You have to recognize that 0 degrees, 273 Kelvin, even 32 degrees Fahrenheit are the same conditions. 1 atmosphere, 760 torrs, or 760 millimeters of mercury, or 14.7 psi are also the same conditions. And you should be able to use this conversion, because this conversion right here will save you a lot of time. Okay, so let's move on. That's the condition of xenon with excess fluorine. You guys know that excess fluorine simply means that the fluorine is not the limiting agent. You have a lot of fluorine, so you have to do your calculation based on the limiting reagent, which is xenon in this case. And the question is, how much xenon fluoride in grams is produced? And I give you the molar mass. So the strategy is to use gas laws. Change this real quick. Gas laws to get the moles of xenon. And we can use PV equals nRT. And we can calculate moles there because we have the pressure, which is 1 atmosphere. We have the volume, which is 2 liters. And we have the temperature, which is 298. So we have all this, and of course we know R, so we can calculate the moles, or we can simply use that 1 mole of any gas equals 22.4 liters, or 22.4 liters equals 1 mole. Once we have the moles of xenon, we can get the moles of fluorine from the fact that it's a 1-to-1 ratio. So each mole of xenon that is required will also react with 1 mole of xenon. Once we have the moles of xenon, then we can get the mass, once we have the moles of xenon, then we can also get the moles of xenon fluoride. Okay, so let me erase this real quick. Fluorine, which is F2, not Fe, okay, is going to react in a 1-to-1 ratio with xenon, and it'll produce in a 1-to-1 ratio xenon fluoride. Once we have the moles of xenon fluoride, then we can get the molar mass. We can get the mass of xenon fluoride using the molar mass, which is 169.3. So that's the strategy that we'll use. Okay, first we calculate the moles of xenon. That moles of xenon will be equal to the moles of xenon fluoride. Then we can calculate the mass of xenon fluoride. So let me clear this out and let me show you how it's done in one-chain calculation. One-chain calculation simply means that I'm going to do it all in one line. So we'll start out with 2 liters, and then we're going to use this idea that 22.4 liters is 1 mole. So the liters will cancel out, and 22.4 liters of xenon is 1 mole of xenon. And then, so this is a dimensional analysis concept. This right here can be gotten from N equals PV over RT. Or we can use this right here because we know it's STP. Whenever you have STP, use that shortcut. It'll save you time. Then we know that for every 1 mole of xenon, we have 1 mole of xenon fluoride. How do we know that? It's a 1-to-1 ratio right here. Okay, this is a balanced equation. Then we can use the molar mass of xenon fluoride and say that 169.3 grams of xenon difluoride is equal to 1 mole. See how simplistic that is, especially if you buy into dimensional analysis. Again, dimensional analysis will be your friend when you get to Chem 200. Okay, it'll be your friend. It'll get you out of a lot of binds if you don't remember the equation, because the units will develop the equation for you. So this is the setup. You just multiply 2 by 169.3 and divide by 22.4. So let's see how this is done. Okay, let me clear this up. Again, I show you that we're going from here to here. And this will give me the moles of xenon. Then from here to here, this will give me the moles of xenon fluoride. And then from here to here, that'll get me the mass of xenon fluoride. So we're using the stoichiometry map in a different area now to do calculations. Here's, I did it the long way here, just to show you that you'll get into the same place. I use N equals PV over RT. Again, you can see that this particular calculation is more involved than 1 mole equals 22.4. But once you get this value, then it's basically the same as we discussed. You use the mole ratio from the balance equation. Then you use the molar mass to calculate the mass of xenon fluoride. Okay. Again, as long as you can calculate moles, you can do stoichiometry. And I hate to be the bearer of bad news, but in solution chemistry, you can also calculate moles. And that'll complete our stoichiometry map. That takes care of the middle section. But that's for either later today or for Thursday. So that's how you solve that problem. Okay, that's how you solve that problem. Using 22.4 liters equals 1 mole sort of gets you to this problem in a quicker way rather than through this. But if you don't have STP, then you have to go through this. If you don't have standard temperature pressure, you're going to have to go through the ideal gas law. And one thing you can always count for when you have gases, you can assume, at least in this class, that you can assume that the gas obeys ideal behavior. Okay. So are you guys, I'm seeing in my discussion board here that you guys are not hearing me. It says right here, your microphone is off. I'm looking at my microphone and it's showing the green symbol on. So give me a holler if you still can't hear me. Okay, great. So let me go ahead and do a problem that you might be doing in lab. This right here, hydrogen can be produced by the reaction of 1.33 grams of magnesium with excess sulfuric acid. Okay, in lab, you guys you're not going to be using sulfuric acid, you're going to be using hydrochloric acid, but it works the same way. It's an acid. And the fact that it's an acid means that the hydrogen will be generated. Okay, and this is a typical stoichiometry problem. Hydrogen is produced by the reaction of 1.33 grams of magnesium with excess sulfuric acid. What volume of hydrogen gas is produced? And here we don't have STP. So when you see a problem like this, write the conditions. And the conditions are the following. And the reason why you want to write the conditions is because you don't want to keep referring to the word problem. It slows you down. You just want to worry about what variables you have to work with. You have 1.33 grams of magnesium. Okay, that's a starting material. You could probably calculate the moles from that. We'll do that later. We have sulfuric acid, and we're calculating the volume of hydrogen gas in this reaction. And if you look at this problem for the first time, you might be asking, what does magnesium have to do with hydrogen? You got to remember that this is a reaction in which hydrogen is produced. If you just look at the numbers and don't understand the chemistry, you're going to get very lost. So it's all about the chemistry. That's why this is a chemistry class. If you understand the chemistry and you can vision what's going on in a problem, you're going to be that better equipped to solve the problem. So we're calculating the volume of hydrogen gas, and it tells you that the conditions are 25 degrees Celsius. Automatically convert that to Kelvin. So no matter what, you have to use the Kelvin temperature. So if you add 273 to this, that's going to be 298 Kelvin. And we have 1.12 atmosphere, and that's good because then we don't have to convert that. That's already in the units that we want. So we have the temperature, we have the pressure, we're calculating the volume. And remember, PV equals nRT. We're calculating this. We therefore need moles. And the moles probably come from the chemical reaction. So again, for those of you who have lab, this is the typical, this is a reaction that you might have. You've got sulfuric acid. That's what it says right here. Hydrogen gas can be produced. That means hydrogen gas is the product by the reaction with 1.33 grams of magnesium. It's a starting material. You have 1.33 grams of this with excess, this is excess, sulfuric acid. What volume of hydrogen gas is produced? If you look at this reaction, you see that this is a single displacement reaction where magnesium bumps off the hydrogen and combines with the sulfate. So your other co-product here is magnesium sulfate. Okay, magnesium is +2, sulfate is -2. So this is the correct formula for magnesium sulfate. The magnesium will bump off the hydrogen. In fact, it'll bump off 2 hydrogen. So this equation is actually already balanced. It's a 1-to-1-to-1 ratio. Okay. So what we need to do is we need to calculate the moles of magnesium. We use the balancing equation to calculate the moles of hydrogen, which will be equal. And then we can use this moles of hydrogen in the ideal gas law to calculate the volume of hydrogen. So that's the strategy that we have here. So let me go ahead and set this up for you so that you guys can see. Remember that the atomic weight of magnesium. Let me just write that down so that you guys can see. The atomic weight of magnesium, right, it's about 24. It's 24.31. So the atomic weight of magnesium equals 24.31. Okay, so what we can do is the following. Let me blank out my screen. We can say that, again, the strategy is moles of well, let me clear that. Mass of magnesium to moles of magnesium. And what do we do there? We use the atomic weight. Then we convert moles of magnesium to moles of hydrogen. And what do we do there? We use the balance equation. Then we can go from moles of hydrogen to volume of hydrogen. And what do we do there? We use PV equals nRT, where V equals nRT over P. That's the strategy that we're going to use. So let's take a look at this one right here. It's 1.33 grams of magnesium. We know that magnesium has an atomic weight of 24.31 grams per mole. So 24.31 grams per mole of magnesium. Okay. You can see that the grams cancel. Then we can see from the balance equation, if you look at your notes, for every 1 mole of magnesium, we have 1 mole of hydrogen. Then we stop there. And the reason why we need to stop there is because we can't do this in a chain reaction. We actually can, but it's going to be more involved. We're just going to calculate the moles of hydrogen here, and then we're just going to plug it in there. We're going to go from dimensional analysis to algebra. Okay, so if we do this calculation, let me get my calculator real quick. What we have is 1.33 divided by 24.31, and that's 5.47 times 10 to the minus 2 moles of hydrogen. Now we can go, the volume of hydrogen is equal to the moles of hydrogen, 5.47 times 10 to the minus 2 moles of hydrogen times R, right here, 0.08206 times temperature. Remember the temperature was 25, so that's 298. Stop there. All over the pressure, and the pressure I said was about 1.12, I believe, okay, atmosphere. So if you do this calculation, let me just, and you guys can follow along if you have a calculator. Take 5.47 times 10 to the minus 2, which should be in your calculator. Multiply that by 0.08206, that's R. Multiply that by 298 and divide by 1.12. And what you get is 1.19 liters. Remember that if you're using R, then the unit is liters, atmosphere, mole, Kelvin. So the volumes will be liters. Liters, atmosphere, mole, Kelvin. The Kelvin will cancel out with that. The moles will cancel out with that. The atmosphere will cancel out with that. And what you get is liters left over. So let's show you what's going on. We're going from here to here to here to here. That's the path that we're taking. We're taking the mass of magnesium, converting it to moles of magnesium to moles of hydrogen to volume of hydrogen. That's the strategy. I just like to point that out because there is an organization involved. And this is basically it. So let's take a look at this right here. Um, what we have is this is the moles. Like we said, it was 5.47 times 10 to the minus 2. Then we converted moles to moles of hydrogen. I'm doing this step by step rather than in a line equation for the first two steps. And then we use this equation right here, PV equals nRT, just like I said. And when we do that, it comes out to 1.19 liters. Here, I think it's asking for milliliters. So just remember that 1,000 milliliters equals 1 liter. That was just the last step. So hopefully you can follow along with that because, again, for those of you in lab, you do a similar calculation or at least a calculation that involves a generation of hydrogen gas. Here's another problem that involves stoichiometry. And whenever you see a problem like this, don't panic, okay? And I know that a lot of you who are frightful of stoichiometry will just shut down. The reason why you shut down is because you tend to be overwhelmed with the information that the question provides. And so rather than start, you just kind of stare blindly at the problem. If you can, start breaking down the information. Get started. Don't just stare at the page. Break it down. Make sure that the equation is balanced. Okay, that's the first thing. And here I can see that I've got 2 iodine, 10 fluorines. 2 times 5 is 10 fluorines. So that's a balanced equation. It's a 1 to 1 to 1. And that's always good. Even if you mess up, you'll still be okay because there's no mole ratio to fix. But understand that it's not a 1 to 1 to 1, it's a 1 to 5 to 1. And the reason why it's 5 is because the fluorine is 5. And it's not a 1 to 5. The equation was already balanced. I take that all back. Just looking at the equation, I was jumping to assumption it's a 1 to 5 to 2. Okay. But that's the mole ratio that you guys are going to have to use when you relate one chemical to the other. It's a 1 to 5 to 2. So let's continue. After we balance the equation and we see the mole ratio, it says a 5-liter container, so the volume is equal to 5 liters, is filled with 10 grams of iodine, excess fluorine, which means that fluorine is a non-factor in this problem except for balancing, and the reaction proceeds to completion. That means it's 100%. Xenon being completely consumed. So this is the limiting agent. In other words, this is the chemical that dictates how much product you produce. After the reaction is complete, the temperature is 125 degrees. So temperature goes 125 plus 273. That's 398 Kelvin. Okay. What is the pressure of IF5 in the gas? So again, the strategy is to convert grams mass of iodine to moles of iodine, which will give you, based on the balance equation, the moles of IF5. It's going to be twice the moles of iodine because it's a 2 to 1 ratio. Okay. Once you have the moles of iodine, then you can use PV equals nRT. You have the volume, and they mention the volume up here. It's in the reactions taking place in a 5-liter flask, and you can assume that the flask is not going to change volume. You have temperature, 298, and you just calculated moles, so you can calculate the pressure. In stoichiometry problems, it's all a condition one type of problem where you have a condition and you have to figure out what the other variables are. Okay. Once we do that, then we can solve this problem right here. We can solve that. The other question here, how many molecules of F2 reacts with I2? That's chapter 8. What mass of IF5 is produced? That's chapter 8. The other two parts is not gas laws. The other two parts is chapter 8. It's going to be straight moles of iodine to moles of fluorine for this one. And then you can use the moles of fluorine and Avogadro's number to figure out the molecules of fluorine. For this one, once you have your moles of iodine, you can get the moles of IF5. And once you have your moles of IF5, you can get the mass of IF5 using the molar mass of IF5. So I'm going to skip this for the sake of time because you guys should be able to do that. Okay, and I think the problem is going to be, the solution is going to be shown to you, but I want to concentrate on gas loss in this particular discussion. So let me go ahead and use this area to show you how to do this calculation. First of all, I'm going to need the molar mass of I2 and the molar mass of IF5. I think I do that in the next page. Here's a strategy by the way of, let me clear this. What we're going to be doing. The strategy is to get the mass of iodine to moles of iodine, moles of iodine to moles of IF5, and then moles of IF5 to pressure. So we're doing that path. So here's the path that I showed you. And in this particular case, I actually did everything here. This part right here is how to calculate moles. Okay, this part right here, let me erase this. This part right here is how to calculate moles. Then I use the moles and T and V to calculate the pressure. So I've sort of put it in a different form. That way you can see how the overall picture is shown. So 10.0 grams of I2. The molar mass of I2 is right here, 253.81 grams per mole of I2. Then we know that for every 1 mole of I2, you have 2 moles of IF5. How do we see that? Right here. It's a 1:2 ratio. This will give me the moles of IF5. Once I do that, then I can calculate the pressure. Using that. Here's my N. Here's my T. So here's my N. Here's my T. Here's my R. Okay. And then divided by volume. Let me see, there's a question. Could you show us how to do the molecular geometry problem on the quiz? With all, let me, please ask me that again towards the end of class, and I'll go back and I'll show you how that's done, okay? The molecular geometry, where I give you the molecule and you have to figure out the geometry. If you had lab, you would have been able to do that particular problem. If you didn't have lab, that would have been a little bit of a struggle, but we went through an example in class to do that, okay? So let me cover that towards the end of class. when I get through this. Okay, so just make sure you raise it. Raise it up at about maybe 2:45. That way I have time to go over it. Or when I finish gas loss, I can go through that. Okay. So here we have this. And once you calculate this, you can certainly calculate the pressure. And if you do this math, you come up with 0.515 atmosphere. Okay, 0.515 atmosphere. So let me go ahead and move on so that you guys can see how this is done. Yeah, clear this. The rest of this is just addressing these right there. Okay, and that's chapter, I believe it's chapter 7 and 8. Actually, chapter 7 is balancing equation, so it's mostly chapter 8. So review this before your final, because that'll be something that you will definitely see in your final. And again, those two last problems has really nothing to do with gas except for this first part, but I want to bring you back to what you guys have already learned so that you don't forget. I'm going to change gears now. And the reason why I'm changing gears is because this is the other concept. The other concept you guys have to know for the lab today. And it's called the Dalton's law of partial pressure. Dalton's law of partial pressure simply tells you that the sum of the pressure of the individual gas is equal to the total pressure. And it seems like a very simple concept, but this is only at constant volume. So delta V, which means that the second volume and the initial volume doesn't change. V2 and V1 are equal, so V2 minus V1 equals 0. That's what delta T means. That is, the volume doesn't change. If the volume does change, then you have to make an adjustment. Okay? So Dalton's law of partial pressure is basically the idea that when the sum of the pressure is additive, it's like if you have a scale. If you have a scale and you add books to it, and let's say that one book is 1.5 pounds, another book is 0.75 pounds, and a third book happens to be 5 pounds. Then the scale is just going to be the sum of those masses. It's going to be 5, 12, 7.25 pounds. Okay? Well, that's basically what we are saying in terms of Dalton's law of partial pressure. The sum of the gas pressure is equal to the total pressure. That's simply what we're saying. So, consider 3 balloons. What is the total pressure of if air is combined in one balloon? So we have 1 liter, 1 liter, 1 liter. And the question is, what is the total pressure? Sorry, when 1 atmosphere, 0.5 atmosphere, and 0.7 atmosphere is combined so that the volume, notice the volume doesn't change. Delta V equals 0. This volume is the same as the other. So it's simple enough. All you do is add the pressure and it comes out to 2.2 atmosphere. And that would be correct in terms of applying Dalton's law of partial pressure. The sum of the pressure is equal to the total pressure as long as the volume doesn't change. Once the volume changes, you gotta apply, you gotta correct for the fact that the volume is not the same anymore. Okay, here's an example. I have 1 atmosphere, 0.1 liters. I have 0.5 atmospheres, 0.5 liters. And the question is, I have 2 balloons. Okay, what is the total pressure if air is combined in 1 balloon? If both of these are combined so that the new volume is 1.5. The strategy here is that you've got to figure out what that new pressure is in this new volume what this new pressure is in this new volume. So you have to use Boyle's law twice. Boyle's law for this and Boyle's law for that. Why? Because when you take 1 atmosphere, 1 liter, and then you put it in 1.5 liters, remember that the volume is bigger. That means the pressure drops. So that pressure is going to change from 1 atmosphere to something lower because now it's in a bigger volume. Here, we go from 0.5 liters to 1.5. Again, that pressure is going to drop because we're going from a small volume to a bigger volume, so the pressure is going to decrease. Remember what happens when we increase, when we make a volume smaller? That means that the gas has less room to run around. It means it's going to collide with the boundaries of the container more frequently. More collisions results in higher pressure. So first thing that we need to do is look at balloon 1. And we need to use P1V1 equals P2V2. And that comes from this right here. PV equals nRT. We're just simply doing this. It's the combined gas law. P2V2 equals N2RT2. In condition 1, the moles are not changing because we're not making the balloon leak. The R is constant and they never mention temperature. So what we have is P1V1 over P2V2 equals 1. So when we put this over here, we have this equation right here. That's Boyle's law. What are we solving? We're solving for the new pressure. Pressure 2 under that new condition is going to be pressure 1, volume 1 over volume 2. So pressure 2 is going to be equal to, in this particular case, 1 atmosphere times 1 liter. That's this right here. Let me clear that for you. Okay, that's that. All over 1.5 liters. And I got 1.5 liters from this right here, the new volume. So when we do that calculation, it's just going to be 1 divided by 1.5, because 1 liters times 1 atmosphere is divided by 1.5. That's basically our calculation. So this is equal to 0.667 atmosphere. We do the same thing for the second balloon, P2 prime, because that's what this is equal to, again, P1 V1 over V2. Now for the second balloon, P1 is 0.5 atmosphere, V1 is 0.5 liters, all over 1.5, because that's still the volume that we have. So this right here for the second balloon is equal to 0.5 times 1.5 divide, and this is 1.167 atmosphere. So we add 0.167 to 0.667, what we get is a new pressure. New total pressure is equal to 0.833 atmosphere. So again, let me emphasize that when you take 1 atmosphere and 0.5 atmosphere, it is not equal to 1.5 atmosphere. And the reason why it's not equal to 1.5 atmosphere is because the volume has changed. You have to figure out what this gas, what pressure this gas will be at that new volume. Comes out to 0.667 atmosphere. What the pressure will be for this gas at that new volume, it's 0.167. Then and only then can you add the two pressure. It happens to be 0.667 plus 0.167, that's 0.833 atmosphere. So that's the math behind all this thing. Let me go ahead and clear this up. And again, this is my math showing it to you in a more presentable fashion. This pressure P2 is basically that. This pressure P1 is basically that. And then you're just adding the two. Okay, you're just adding two. This is this. This is this. And what you get is the total pressure. It comes out to 0.833, just like we said. Here's another example of Dalton's law of partial pressure. We have the sum of the partial pressure is equal to the total pressure. Okay, so if you break it out to P is equal to nRT over V, and what you have here is that the T is constant, but the moles are different amount of gas. What you can do is you can factor these guys out. Don't worry about the math. Just make sure that you understand how to apply the final equation. Okay. We basically have this. What we have is this plus this is equal to the partial pressure. And what we're doing now is we're going to simplify this. We're going to factor out RT over V. And what we have now is the total pressure of two gas combining, as long as the volume is constant, but the amount is different, is we add the 2 moles. So we have the total moles in that container. And then we just use RT divided by P. So that's a simple equation you can use in gas laws. If you're taking a container and you're pumping in different amounts of gas, like oxygen and nitrogen and water vapor, and you know that the volume is fixed, and you know that the temperature is constant, all you need to do is know the moles of each one of these, plug it in here, and then you can get the total pressure. Because what you're essentially doing is this right here. You're adding the partial pressure of water to the partial pressure of nitrogen to the partial pressure of oxygen. Except you're simplifying the math because RT and V are all the same. So why do the calculation 3 times with RT over V when you can just add the total moles and multiply by RT over V? And that's basically what this equation gives you right here. The total pressure is equal to RT over V times the sum of the total moles in that container. Okay. This right here is what we call a mole fraction. And that's something that you guys will cover in 200 in more details. For now, just worry about this. Okay. But know that in Chem 200, you probably see something called the mole fraction. So here's a problem in which we apply this concept. It says 2 liter, so we have a volume, and that's 2.0 liters, contains 0.0125 moles of oxygen, 0.00325 moles of helium. Temperature is 15 degrees. Add 273 to that automatically, that way you don't forget. That's 288 Kelvin. What are the partial pressure of these gas and what is the total pressure? The partial pressure is easily done. You can just do this. P equals N RT over V for oxygen. P equals nRT over V for helium. And then the total pressure is just going to be combining these two, okay? Or you can calculate the total pressure by just saying that that is equal to moles of oxygen plus moles of helium, RT over V. So let me just show you that real quickly in the next slide. That way you can see that calculation rather than me drawing it up. Let me clear this. Here's the variables. Here is oxygen. Here is helium, just like I said it would be. Here's the calculation. This is the moles of oxygen. This is R. This is T. Remember, T is 288 all over V, 2 liters. So we can calculate the partial pressure of oxygen. We can calculate the partial pressure of helium. And then the total pressure is just the two combined. Okay? Or we can simply do this. The moles of oxygen plus the moles of helium times RT over volume. These two agree with each other. These two agree with each other. So hopefully you guys are sort of being, you have enough, I do enough grilling so that you guys are able to do these calculations without my coaching. This is the last concept that I will talk about. And again, it has to do with Dalton's law of partial pressure. And this, more than anything, is related to the lab today. So for those of you who have lab today or Thursday, this is what's going to happen. You guys are going to be reacting magnesium with hydrochloric acid, and you're going to be generating hydrogen gas. But you just can't generate hydrogen gas without collecting it, because you have to collect the hydrogen gas in order to measure its parameters, what the pressure is, what the volume it is, so that you can calculate R. Remember that in this particular lab, you are calculating R, and R is from PV equals nRT. So we rearrange this equation. R is equal to PV over NT. So what we need is the pressure of the hydrogen gas, the volume of the hydrogen gas, the moles of the hydrogen gas, and the temperature of the hydrogen gas. And then we can calculate experimental value. This is an experimental value of R. The difficulty of this particular experiment is, how do we calculate the pressure? Because what we're doing is we're going to be generating hydrogen gas. Usually what you have is you have this is what it's going to be like if you did this experiment. You guys would be taking a test tube. You're going to have some HCl in here. You're going to cover that test tube, and you're going to have a tube that comes off. Then you're going to open up this tube, and you're going to drop a strip of magnesium into that hydrochloric acid. That hydrochloric acid is in excess. This is the limiting. So the moles of the magnesium will give you the moles of the hydrogen. That's how you calculate that right there. Okay. This reaction takes place in here, and then it's going to release hydrogen gas. So the hydrogen gas is going to come out this tube, and it's going to be collected over water. The problem with collecting over water is that not only do you collect hydrogen gas in here, you also collect water vapor. So it's not pure. Okay, it's not pure. So you have to correct for the water vapor, that is collected alongside the hydrogen gas. So how do you do that? Well, the thing is that the total pressure in this container is equal to the partial pressure of hydrogen plus the partial pressure of water, because those are the two gas components that you're collecting. The total pressure is the same as the atmospheric pressure, because the pressure outside is equal to the pressure inside. So we use a barometer to read the total pressure. Then we use a table. Depending on the temperature, water has a certain vapor pressure. If the temperature was 373 Kelvin or 100 degrees Celsius, then that vapor pressure of water would be 1 atmosphere. Essentially, you're boiling water. But the temperature is not 100 degrees Celsius. The temperature is not 373 Kelvin. It's going to be the temperature that you record when you do this experiment. So you're going to determine what that vapor pressure of water is, because they give you a table. They give you a table of the vapor pressure of water depending on the temperature. Okay? And that table is in your lab book. And so all we've got to do now, in order to calculate the partial pressure of hydrogen, which is what you want to use in this equation right here, is we take the partial pressure of hydrogen is equal to the total pressure, which is our barometric pressure, minus the partial pressure of water. We have to correct for it. We have to subtract the pressure due to the water from our total to get the partial pressure of hydrogen. Once we got the partial pressure of hydrogen, then we have the P, we have the V, we have the T, and we calculated the N. So that's what this problem is about. Okay, this problem, more than anything, is very related to the experiment that you guys are having today. And you'll probably hear me do this problem again in lab, but it never hurts to hear something twice. So let me clean this slate, okay, and show you what's going on. Here is the temperature is 21 degrees. So you go to a vapor pressure table. I think you might have one in the back of your lab manual. If you don't have that, then in the context of your lab manual, they give you the vapor pressure. The vapor pressure of water at 21 degrees, this is millimeters of mercury. So in order to convert it to atmosphere, you got to remember that 760 millimeters of mercury equals 1 atmosphere. You just have to do a conversion. But this is the partial pressure, 18.650. So we have to subtract that from the total. And the total is 760. That's what they tell you. So we have to convert this millimeters of mercury to atmosphere so we can subtract it from 1 atmosphere. Or we can just take 760 and subtract 18.65, and that'll be in millimeters of mercury, and then convert that to atmosphere. The reason why you need to convert this to atmosphere is because, again, we're calculating R. R is in atmosphere. So let me go ahead and clear this. Here it is. I've subtracted 18.65 from 760. This is my pressure due to hydrogen. And then now I can use this to plug into my ideal gas law. So let me just show you that real quickly. Actually, I don't have enough here, but that's how you would correct for the partial pressure of hydrogen, because you're collecting over water. Okay, so you got to do this calculation in the lab. I'm going to stop there because I think I've completed the gas law problems. This is just a summary, and these are all the gas law problems we've covered. We've covered Boyle's law right here. We've covered Charles' law, we've covered Avogadro's law, we've covered Gay-Lussac's law, but you don't have to remember these laws because it's all in the combined gas law. And the combined gas law is actually derived from the ideal gas law. And then we have Dalton's law of partial pressure. We never covered that, so don't worry about that. It's not in your book. Um, in general chemistry 200, you will cover that. But in this class, don't worry about Graham's law of diffusion. Okay.